Right, diving in today, folks, we're going to tackle something pretty cool, similar geometric figures. But specifically, we're going to zero in on triangles,
Yeah.
right? And our goal, with this deep dive is to really give you a solid understanding of how this all works. Because it turns out it pops up in some really surprising and useful ways out there in the real world.
Yeah, for sure. When we're talking about similar geometric figures, and especially triangles, we're not just dealing with abstract shapes on a chalkboard. I mean, this concept, it's kind of baked into how we understand and interact with, like, the physical world around us. From the maps we use to get around to the blueprints that architects use to design buildings, it's everywhere.
So let's just start with the basics then. What does it even mean for two shapes to be similar, right?
Yeah.
What's the core idea there?
Well, you can think of it like this. Similar shapes, they have the same fundamental form, right? The same basic look. But the catch is they might be different sizes. Like, picture two circles in your mind, okay? One is tiny, maybe the size of a dime, and the other is huge, like a giant Ferris wheel. They're both still circles, right? Same shape, just totally different scales.
So the shape is the constant, the size can be all over the place.
I like that. Exactly. And it's not just circles. This holds true for all squares, all equilateral triangles, you name it. You look at the angles, they're all identical. And the proportions, how the sides relate to each other, that's the same too.
Okay, that makes sense. Now, our source material, it also mentions these things called congruent figures.
Yeah.
How do those fit into the picture?
Good point. Congruence, that's like similarity on steroids,
Yeah.
It's a more specific condition. A congruent figure, so the same shape and the same size, think of it like two identical floor tiles, right? They're congruent, perfect copies. Now here's the key. If two figures are congruent, they're automatically similar too, right? Because obviously they have the same shape. But it doesn't work the other way around. Two triangles, they can have all the same angles and have proportional sides that makes them similar. But they could still be different sizes, so they wouldn't be congruent.
Got it. So congruent is like identical twins, while similar is more like a parent and child, right? Same basic features, but different stature, I guess.
Yeah, perfect analogy.
Okay, now this whole idea of similarity, it's not just a theoretical thing, right? The intro to our deep dive here, it brought up some pretty big questions, like how do scientists actually measure the height of something like Mount Everest or the distance to the moon? I mean, they can't just climb all the way up there with a tape measure, can they?
Exactly, and that's where the power of similarity, it really comes into play. These seemingly impossible measurements, they rely on something called indirect measurement. And a lot of times it boils down to creating and analyzing similar triangles.
Okay, walk me through this.
So let's say you want to measure the height of a tall tree, right? You don't have to climb it. You can measure the length of its shadow on the ground, then measure the length of your own shadow. Now, because the sun's rays are hitting you and the tree at the same angle, you've basically got two similar triangles. One is the triangle formed by the tree, its shadow, and the sun's rays. The other is the triangle formed by you, your shadow, and the sun's rays. And since they're similar, the ratios of corresponding sides are going to be the same. The length of your shadow and your height, you measured the tree's shadow, so boom. You can use those ratios to calculate the height of the tree. It's all about proportions.
That's really cool. I never thought of it that way.
Yeah, and it goes way beyond trees. The same basic principle, using similar triangles and proportions, it's how we figure out the distances to stars, and the size of planets. It's pretty wild when you think about it.
So even something as seemingly abstract as similar triangles, it's actually helped us unlock these huge secrets about the universe. That's amazing. Now the intro, it also mentions some more everyday uses for this stuff, like in map making and blueprints. How does similarity come into play there?
Well, think about a world map, right? It's basically a tiny little representation of this giant curved surface. And similarity, it's what allows map makers to accurately show, the shapes of the continents and the relative distances between them. It all comes down to proportions.
Right, obviously Greenland isn't actually that big compared to Africa, right?
Yeah, exactly. The map has to maintain the right proportions so it doesn't distort our understanding of the real world. Same thing with blueprints. Architects, they create these scaled-down drawings of buildings, making sure that all the parts are proportionally represented. So when builders follow that plan, the final building, it ends up having the correct form and dimensions.
And what about photographers, when they make those prints of different sizes from the same negative?
Perfect example. Whether it's a teeny-tiny wallet-sized photo or a big 8x10, the image, it's essentially just a scaled version of the original. Similarity ensures that the proportions, the relationships between the different elements in the picture, they stay the same.
Okay, so we've got this good kind of intuitive understanding of what similar shapes are all about. But let's get a bit more, I don't know, formal about it. How do we actually define similar polygons in, like, mathematical terms?
All right, so for two polygons with the same number of sides to be considered similar, they have to meet two very specific conditions. First, all the pairs of their corresponding angles, those have to be equal. And second, the ratios of the lengths of their corresponding sides, those also have to be the same. And that constant ratio, that's what we call the scale factor.
So it's a two-for-one deal, right? It's not enough for just the angles to be equal
Yeah.
or just the sides to be in proportion. It's going to be both, right?
Exactly. One without the other, it doesn't guarantee similarity. Our source material, it actually has this really neat visual way to demonstrate this with something they call Activity 1, the shadow experiment. Imagine you're shining a light on a cardboard cutout of, say, a quadrilateral, right? The shadow that it casts. That's an enlarged, similar version of the original.
Right, because the light's coming from a single point, so it's expanding outward.
Exactly. And the points and lines of the original shape, they correspond directly to the points and lines in the shadow. And if you measure, you'll find that the sides of the shadow, they're proportional to the sides of the original shape. It's a cool way to see the definition of similarity in action.
I like that the shadow's the same shape, just blown up bigger.
Yeah.
Now, I remember that the source, it also gave us some examples of what happens if only one of those conditions is met, right? To really drive home the point. Can you walk us through those?
Sure. So let's picture a square and a rectangle. Okay.
Yeah.
Both of them, they've got four right angles, so all their corresponding angles are equal. But if the rectangle sides aren't in the same proportion as the square sides, which they won't be unless it's actually also a square, then the shapes are not similar. Think of a square that's 1 inch by 1 inch and a rectangle that's 1 inch by 2 inches. Same angles, but clearly they don't have the same shape.
Right.
Now, going the other way, imagine a square and a rhombus, that diamond shape where all the sides are equal. In this case, all the sides can have the same ratio, but if the angles of the rhombus aren't 90 degrees, then it's not going to be similar to the square. So these examples, they really highlight why both parts of the definition, the equal angles, A and D, the proportional sides, they're both absolutely essential.
Okay, those examples really make it crystal clear why we need both pieces of the puzzle. Now let's narrow our focus even further. Just zoom in on triangles specifically. Yeah. Does that same two-part definition still hold true?
Oh, absolutely. A triangle is just a polygon with three sides, right? So for two triangles to be similar, their corresponding angles have got to be equal, and their corresponding sides have got to be in the same ratio. No exceptions. Now, when we have two triangles and all their corresponding angles are equal, we call them equiangular triangles. And this is where things get really interesting because it brings us to a super important discovery made by, the OG of geometry, the ancient Greek mathematician Thales.
Ah, Thales.
Yeah.
The legend. What did he figure out about these equiangular triangles?
So Thales, he observed this fundamental truth. If two triangles are equiangular, meaning all their corresponding angles are equal, then the ratio of any two corresponding sides is going to be the same. This is like a cornerstone of everything we know about similarity. And it's all tied up with this really important idea, the basic proportionality theorem, which, some people even call Thales' theorem in his honor.
Okay, that sounds important. Break down this basic proportionality theorem for me. What does it tell us?
All right, so Theorem 6.1, it states that if you draw a line that's parallel to one side of a triangle and that line intersects the other two sides at different points, then it divides those two sides proportionally.
Okay. Visualize, everybody. We've got triangle ABC, and we draw a line, DE, parallel to the base, BC. DE slices through AB and AC. Now, what's the big takeaway here?
The big takeaway is that the ratio of the length of AD to the length of DB, that's going to be equal to the ratio of the length of AE to the length of EC. So those parallel lines, they essentially create these proportional segments.
Parallel lines, equal ratios.
Got it. Now, didn't we also talk about a flip side to this theorem, the converse?
Yeah, you're right. Theorem 6.2, the converse, basically says that if a line divides two sides of a triangle in the same ratio, then that line must be parallel to the third side. It's like the opposite of Theorem 6.1. If the proportions are there, then the line's got to be parallel. So it works both ways. Parallel lines imply proportional sides, AD proportional sides imply parallel lines. It's a two-way street.
Da-da.
Now, our source material gives us a bunch of examples of how these theorems actually get used in practice. We're going to go through a couple of those.
Definitely. Example 1, it shows that if you've got DE parallel to BC in triangle ABC, then the ratio of AD to AB is going to be equal to the ratio of AE to AC. And this just builds directly on theorem 6.1 with a little bit of algebra thrown in.
So if you know the basic proportional relationship from the theorem, you can just rearrange things a bit and boom, you get this new relationship.
Precisely. And then there's example 2, which deals with the trapezium, that shape with one pair of parallel sides. We've got trapezium ABCD, where AB is parallel to DC. And there's another line, EF, running through it, also parallel to AB.
Okay, picture a trapezoid with a line cutting through the non-parallel sides.
Yeah, and the goal is to prove that the ratio of AE to ED is equal to the ratio of BF to FC. And the trick here is to draw a diagonal line, AC, which divides the trapezium into two triangles.
Ah, the classic divide and conquer strategy. Break down the complex shape into simpler ones.
Exactly. And now you can apply theorem 6.1 to each of those triangles separately, using the parallel lines to establish proportional relationships. And then, with a little bit of clever manipulation, you can link those relationships together and prove that the ratios we're interested in, AE to ED and BF to FC, they are indeed equal.
That's neat. And didn't one of the examples also show how we can use these ideas to prove that a triangle is isosceles?
Yeah, example 3. So in triangle PQR, we're given this proportional relationship PSSQ equals PTTR. And we're also given that angle PST is equal to angle PRQ. Now, using the converse of the basic proportionality theorem, that's theorem 6.2, the proportional sides tell us that the line ST must be parallel to QR.
Proportional sides, parallel lines.
Right. And because those lines are parallel, certain angles in the triangle must also be equal. Those are called corresponding angles. So we combine this knowledge with the angle equality we're given, and we can deduce that two angles of triangle PQR are equal. And if two angles of a triangle are equal, well, by definition, it's gotta be an isosceles triangle.
Excellent. So these theorems, they're like the foundation for proving all sorts of other geometric relationships. But now let's go beyond just those relationships within a single triangle and talk about how we determine if two separate triangles are similar. We don't always have to check all 6 conditions, do we? Like all 3 angles and all 3 sides.
Nope, definitely not. Just like with proving triangle congruence, we've got some handy shortcuts for establishing similarity. The first one is AAA similarity, that stands for angle-angle. It's theorem 6.3.
AAA, easy to remember.
Right. And it basically states that if all 3 pairs of corresponding angles in 2 triangles are equal, then those triangles, they've got to be similar. The cool thing is, if the angles are all matching up, the sides will automatically be in proportion too. It's like a package deal.
Now, I remember the source talked about a proof for this that involved, like, building a smaller triangle inside a bigger one. How does that work?
All right, so picture 2 triangles, ABC and DEF, with all their angles matching up. We can take triangle ABC and basically create a copy of it inside DF. This copy, we'll call it DPQ. We make sure that DP has the same length as AB and DQ has the same length as AC. Now, because all the angles are equal, this little triangle DPQ, it's going to be oriented the same way as DEF. And this construction, it forces PQ to be parallel to EF. Then, using our trusty basic proportionality theorem on triangle DEF, we can show that the sides of DF are proportional to the sides of ABC.
Okay, so by building that smaller congruent triangle inside the bigger one, we can use the parallel lines and the basic proportionality theorem to prove the whole thing. Clever. And then there's that super useful offshoot of AAA, right? The AA similarity rule.
Oh yeah, that's a lifesaver. The AA corollary, it tells us that if we can just show that 2 pairs of corresponding angles are equal in 2 triangles, then bam, we know the triangles are similar. And the reason this works is if 2 angles of one triangle match 2 angles of another, well, that third angle in each triangle, it has to be equal too, right? Because all the angles in a triangle have to add up to 180 degrees. So checking 2 angles is enough to guarantee that all 3 are good, and therefore the triangles are similar.
Much easier than checking all 3. All right, so we've got AAA, or AA, based on angles. What's the next shortcut for proving triangle similarity?
Next up is SSS similarity, which stands for side, side, side. This is theorem 6.4. And it basically says that if the lengths of all 3 pairs of corresponding sides in 2 triangles are in the same ratio, then, again, those triangles have got to be similar. So just by checking those side ratios, we know they've got the same shape.
It's kind of wild that just knowing the side ratios are equal is enough to guarantee the angles will be equal too, right?
It is. And the proof for this one, it uses a similar approach to the AAA proof. You create a triangle congruent to one of the triangles inside the other one using those proportional side lengths. And by showing that this constructed triangle fits in perfectly angle-wise, you can prove that the original two triangles are indeed similar.
Okay, so we've got AAA or AA, which uses the angles. We've got SSS, which uses the sides. What's the last big similarity criterion?
The last one is SAS similarity. That's side angle side. It's theorem 6.5. And this one is a bit of a hybrid because it uses both sides and angles. It says that if one angle of a triangle is equal to one angle of another triangle, and indeed the sides that form those angles are proportional, then you guessed it, the triangles are similar.
So it's like the SAS congruence rule, but instead of needing the included sides to be equal, they just need to be in the same ratio.
That's exactly it. And the proof, again, it involves building a congruent copy of one triangle inside the other, using that given angle equality and the proportionality of the sides next to that angle. And this construction, it leads to parallel lines, which ultimately proves the similarity.
These criteria, they're definitely a lot more efficient than having to go all the way back to that original definition every time. Now, the source, it gives us a bunch of examples of how to use these shortcuts in practice. Want to run through a few of those?
Sure. Example 4, it shows two triangles, POQ and SOR, where PQ is parallel to RS. And we can prove that they're similar using AA similarity. Those parallel lines, they create equal alternate interior angles, so angle P is equal to angle S, and angle Q is equal to angle R. And the triangles also share that vertically opposite angle at point O. Two pairs of equal angles, boom, similar triangles.
Nice and straightforward. How about example 5? That would involve figuring a missing angle, right?
Right. So in example 5, we're given the side lengths of two triangles, ABC and PQR. And if we look closely, we can see that the side lengths of triangle ABC are proportional to the side lengths of triangle PQR. It's super important to match up the corresponding sides correctly.
Right, got to make sure you're comparing apples to apples.
Exactly. And this proportionality, it tells us right away that the triangles are similar by SSS similarity. And because they're similar, we know their corresponding angles have got to be equal. So we can calculate the angles of triangle ABC, and then, bam, we automatically know the angles of triangle PQR in the corresponding order.
And example 6, it threw a bit of algebra into the mix with that relationship between the products of side lengths.
Yeah, so in that one, we're given this equation, OA times OB equals OC times OD. And with a little bit of rearranging, we can turn that into a proportion. OA divided by OC equals OD divided by OB. We also know that angle AOD is equal to angle COB because they're vertically opposite angles.
Right, they're formed by those intersecting lines.
Exactly. So what do we have? We've got one angle equal, and the sides that form that angle, they're proportional. It's a perfect setup for SAS similarity. So triangle AOD is similar to triangle COB, and all their corresponding angles are equal.
So we used a bit of algebra to turn a product into a proportion, and then we were off to the races with SAS similarity.
Yeah, exactly.
Now, example 7, that was a classic word problem with the lamppost and the girl's shadow. I remember those from school.
Yeah.
How does similarity help us solve that kind of problem?
Oh, that's a perfect example of AA similarity in action. So you've got the lamppost, which is vertical, making a right angle with the ground. And then you've got the girl, also vertical, making another right angle. And the light from the lamppost, it's casting shadows, which forms two right-angled triangles. And these triangles, they share a common angle at the tip of the shadow. So two pairs of equal angles. Boom. Similar triangles. And once we know they're similar, we can set up a proportion between their corresponding sides, the height of the lamppost to the height of the girl, the length of the lamppost shadow to the length of the girl's shadow, and we can use that proportion to solve for whatever length is missing.
Classic geometry problem. And similarity gives us a neat and elegant way to solve it. Now, there's one more example. Example 8 that dealt with medians in similar triangles, right?
Yep. So a median, that's a line segment drawn from a vertex of a triangle to the midpoint of the opposite side. And what example 8 shows is if you've got two similar triangles and you draw in their corresponding medians, then the smaller triangles that are formed are also going to be similar. And not only that, but the ratio of the medians, it's going to be the same as the ratio of the corresponding sides of the original triangles.
So the similarity, it kind of ripples down to those smaller triangles within the bigger ones.
Yeah, exactly. And the proofs for all of this, they rely on using those fundamental properties of similar triangles, the proportional sides, the equal angles, along with the definition of what a median is. Like, to prove that the smaller triangles are similar, you can use SAS similarity. It all ties together.
So that wraps up the examples, but I do remember the source making a quick mention of one more thing, the RHS similarity rule.
Yeah.
It sounded like that was specifically for right-angled triangles.
Yes, the RHS similarity criterion. It stands for right hypotenuse side. And it's a pretty handy shortcut, but it only works for right triangles. Basically, it states that if the hypotenuse and one corresponding side of two right triangles are proportional, then those triangles, they got to be similar.
Okay, so it's a specialized tool just for right triangles. Good to have in the geometry toolbox, though. Well, I think we've really covered a lot of ground here. Can you give us a quick recap of the key ideas we've explored in this deep dive into similarity?
Absolutely. So we started by understanding the definition of similar figures, same shape, potentially different size, and how that differs from congruent figures, which are both the same shape and the same size. Then we dove into the basic proportionality theorem and its converse, which established that beautiful connection between parallel lines and proportional sides within a triangle. And finally, we explored those super useful AAA or AAA, SSS, and SAS criteria, which give us shortcuts for determining if two triangles are truly similar.
And we saw how all of these, seemingly abstract concepts actually have some pretty amazing applications in the real world.
For sure. I mean, from measuring incredibly tall mountains and vast distances in space, to creating accurate maps, blueprints for buildings, and even scaling photographs, similarity is at play all around us. It's one of those fundamental concepts that helps us make sense of the world.
This has been a really fantastic deep dive. To leave you, dear listener, with a final thought. We've mostly focused on geometry here, but think about how these principles of scaling and proportional relationships might show up in other areas. Could those core ideas of similarity be at play in fields like art, design, even in data analysis, where you're often dealing with scaling and proportions? What other unexpected places might similarity be lurking? It's fun to consider how these fundamental geometric concepts, they might be subtly shaping our understanding of the world in ways we don't always consciously realize. Thanks for joining us.